Today, we're going to be going over the cycle of a star, how the mass of that star at a stage will change where it's headed, and how we go from something like a cloud of gas and dust to a protostar, to a main sequence star, growing into a red giant, and where even black holes come from. Now, these spaces in between stars, I'm talking about general space here, is not actually just empty space. We would call this the interstellar medium. It has clouds of gas and dust everywhere, 99% gas in fact, and 75% of it's all hydrogen. This is why stars are using hydrogen within their nuclear fusions. So, at the start of it, we start with a nebula. Nebulae are just vast clouds of hydrogen, helium, and dust. And small fluctuations in density allow gravity to overcome internal pressure, causing regions of the nebula to collapse under their own weight. As the cloud contracts, gravitational potential energy is converted into heat, forming a dense core, known as a protostar. A protostar is the early stage of a forming star. Gravity continues to pull matter inward, raising temperature and pressure within the core. When the core temperature reaches roughly 10 million Kelvin, then hydrogen fusion ignites. This makes the birth of a main sequence star. The main sequence stage is the longest and most stable period in a star's life. During this time, hydrogen nuclei fuse into helium inside of the core, releasing enormous amounts of energy when these energy photons bounce off of the reaction. This energy creates an outward radiation pressure that balances the inward pull of gravity, and this is the state known as hydrostatic equilibrium that keeps a star stable. The more massive the star, the faster it consumes the fuel that it's creating, so it leads to a shorter lifespan. Once the hydrogen in the core is depleted, fusion ceases there, causing the core to contract under gravity. As it contracts, heat generated from the gravitational compression ignites a shell of hydrogen around the core. This shell burning pushes the outer layers outward, expanding the star into a red giant or even a supergiant, depending on the mass. If at this stage the star is still less than 10 times the mass of our sun, then the helium in the core is exhausted, but the star still lacks the temperature required to fuse the heavier elements. Because of this, the outer layers are expelled as a planetary nebula, leaving behind a dense core, known as a white dwarf. White dwarfs are supported by electron degeneracy pressure, preventing further collapse. Over time, they cool and fade. If part of a binary system, a white dwarf can accrete matter from its companion. So within this binary system, the extra mass that's getting fed into this little white dwarf exceeds its electron degeneracy and it fails, causing a type 1a supernova. Well, now we kind of understand how a star's life goes for low mass stars. But what about these really big and high mass stars? Well, if a star is bigger than 10 times the mass of our sun, then these massive stars evolve a little bit differently near the end. Their cores reach the extreme temperatures needed to fuse progressively heavier elements. So this carbon and oxygen keep on doing reactions until it reaches iron. Fusion stops at iron because it does not release energy the same way that main sequence star fusion creates energy for itself. So without outward pressure from fusion, that hydrostatic equilibrium will collapse catastrophically. The rapid core collapse triggers a rebound shock wave that ejects the star's outer layers in a type 2 supernova explosion. The outcome depends on the remaining core mass. If the core is between 1.4 and 3 solar masses, it becomes a neutron star, supported by neutron degeneracy pressure. This is very similar to the electron degeneracy pressure, except it's with neutrons instead of electrons. If it exceeds about 3 solar masses, then gravity overwhelms all resistance, forming a black hole. Alright, so we went over the main sequence of a star's life and even different routes it can take. I know that it's a lot of information, just doing an overview of it. So I wanted to touch on some definitions that might be foreign. So the electron degeneracy is occurring when a star's nuclear fusion stops and there's no more outward pressure from fusion to counter gravity. But gravity is still there. As the core collapses, the electrons get forced into a smaller and smaller volume. So when all the low energy states are filled, any new electron being squeezed in must occupy a higher energy state, even if there's no thermal energy driving it there. So those high energy electrons are moving extremely fast, and their momentum creates an effective pressure that pushes outward. This is not thermal pressure, it's just purely a quantum effect, which I actually find really interesting. Even if the white dwarf were cooled to near absolute zero, this pressure would still be there, and would be able to counteract gravity. So, relating this back to what we talked about briefly when going over the whole star cycle, in a binary star system, if there's this white dwarf, aka a low mass star near the end of its life, getting more and more mass by accretion from its binary star feeding and overflowing into the white dwarf. This pressure becomes too much on the electron degeneracy, and electron degeneracy says this is too much and just implodes and causes a type 1a supernova explosion. Well, now we kind of really understand that the life of a star is a delicate balance between gravity and pressure. From its formation in a collapsing nebula to its final state as a white dwarf, neutron star, or black hole, each stage reflects the interplay of fundamental forces in nuclear physics. While the details vary with mass, all stars follow the same grand cycle, born from cosmic dust, living as radiant furnaces, and ending as remnants that seed the next generation of stars. Thanks for watching.